Okay, these are problems from the packet that I gave y'all. The packet that's like covers the whole unit in terms of definitions, equations, etc. There were just a few problems related to work that I wanted to go over. So, um, this is an example of using like a free body diagram and getting your F net on an object. To get your work. So this object's got multiple forces acting on it. Like it's got an applied force in this direction, it's got an applied force in the opposite direction, it's got another applied force at an angle, it's got a force of gravity. I guess that's what this is supposed to denote, pointing downwards. It's moving a displacement, so there is work being done on it. Okay. Um, and this one's a little weird, but it just kind of goes through a few example calculations. And so I wanted to show it. So, how we would calculate the work for each of these forces. Okay, so force one is actually at an angle to this displacement of like 104. If we look at this angle here, okay, because I want to think about my displacements in this direction. Okay, so I need this angle between the force and the displacement. This force is really pulling against my displacement. Okay, so we're going to end up with a negative work value there. We'll do our force, which is this value, 50 newtons, times my displacement of 2, and then the cosine of 104 is actually minus 0.24. Okay, so that's where my negative work comes in. And I would expect that because this is a force against my displacement. Okay. Then I've got this force. This is kind of a normal force we would expect an applied force, 7 newtons times 2 meters. Force is parallel to displacement, so I don't have any cosine considerations there. So I get 14 joules. This, almost seems like a force of friction back to me. Okay. So 1 newton times 2 meters times cosine of 180. I used 180 there because this is in the exact opposite direction of the displacement. So that's 180. And we got 104 earlier because we were given this angle as 76. Just, I forgot to mention that, but anyway, so 1 times 2 times cosine of 180 gives us minus 2. Cosine of 180 is minus 1. So then force 4 is actually perpendicular to the displacement. So that makes that one 0. Because remember, cosine of 90 is 0. Okay. And then in the end, to get my net work, I add up all of these that I've calculated. I end up with a negative net work. Okay. So even though this thing is moving and it's got a displacement, the forces opposite the movement are greater. They contribute more to work than this force does once you figure out all the math. I can't think of a real life example of this, so we'll move on. But I just wanted to kind of go through the calculations for that. Okay. Then another one for this free body diagram, indicate which forces do positive, negative, or no work. Okay. So here we got somebody pulling an item at an angle. They're pulling it with a tension. It's moving along a horizontal surface. So we've got a force of gravity. We've got a normal. Those would offset each other. And then we've got friction. Okay. And this is a scenario we looked at a long time ago when we did dynamics. Okay. So forces that would do no work are going to be the ones perpendicular to the motion. The motion is this way. Okay, so like this piece right here of tension is what's causing it to move. That's offset by friction. Anything perpendicular at a 90-degree angle to that is going to be zero work, because that's going to give me zero when I solve it out. So normal force is going to be no work. Force of gravity is going to be no work. And the Y piece of my tension, this little piece right here, is going to be no work. Positive work is going to be the X piece of tension. Okay. And then force of friction is actually going to be a negative work, because it's going to be pulling in the opposite direction. Okay. Okay, then we've got a graph here of a force versus a position, which would be like a force versus displacement. We want to determine the work done. So that means we need to get some area under the curves. We got two sections here, okay? This first section, I would do 40 times 2 to get my area, because this is just a rectangle. So I can do length times width. So I get 80 joules there. And then my bottom section, I've got minus 20 times, let's see, it looks like it goes from 2 to 8. So times 6 is minus 120. So again, here I end up with negative work in this example. But that's just really more to explain how we did the area under the curve. We just took the area of these two shapes and added them together. Okay. I think there's a couple of power problems. Let's see. Oh, I need to finish this one. Yeah, there's just one power problem. So, okay. So this is another stairs one. A 60-kilogram student climbs a 3.5 meter flight of stairs in 330, that should be seconds. And we want to know the power exerted. So their work is going to be their weight, m times g, times the displacement or the height. Okay, so that's going to be 60 times 9.8 times 3.5 was the height. That gives me 2,058 joules. Okay. And then if I want power, I'm going to take that work, 2,058 joules, divide it by 330 seconds. And that gives me 6.2 watts. So that's the power exerted by the student. Okay. Okay, and then otherwise for the packet, it's really just like summary statements and definitions and stuff. I'm not going to go through all those in a video. I think y'all can figure those out. I just wanted to do the couple of work problems and the area under the curve, and then this power problem.